Okay, so we're going to look today at this concept of reduction. And reduction is a concept I first learned in the context of functional programming. And it's important in parallel programming. It's important in distributed programming. You've seen that in your uh, assignment 2 and 3. And Chris, did you have a question? Okay. So to bring out the concepts, a declarative language would be better. So I'm going to look at reduction in the context of OpenMP, which is actually a very important practical. Okay, so we're going to look today at this concept of reduction. And reduction is a concept I first learned in the context of functional programming. And it's important in parallel programming. It's important in distributed programming. You've seen that in your uh, assignment 2 and 3. And Chris, did you have a question? Okay. So to bring out the concepts, a declarative language would be better. So I'm going to look at reduction in the context of OpenMP, which is actually a very important practical. So we did OMP before midterm, and we didn't quite complete the things I wanted to talk about. So just to remind you, that was a while ago. You've learned of how to do parallel programming uh, with imperative constructs, and here we see parallel programming being done declaratively. So this is our Hello World program done in parallel, essentially. So what we're doing is not printing out Hello World, because it doesn't make sense to print out Hello World twice or multiple times. We're printing out the next random number. Okay, and we are printing it out with using multiple print statements, and these are not thread safe. So we go and first tell OMP using declarative constructs that we want two threads to execute the next statement block or the next statement. This happens to be anything within curly braces is a statement block. And we want it to, since the print is not thread safe and we want our prints not to be mixed together, we say OMP critical. Okay, so this, you've seen how to create threads, you've seen how to create synchronized blocks in Java. So this is essentially giving you a higher level mechanism to do so. And we've seen here two attributes, parallel and critical. And there's also a number of threads. And we've understood what barriers are in our implementation of A2. And section also we saw earlier, and we saw barrier in the context of OMP earlier also. So we won't be actually looking at these three things today. Okay, so we'll be focusing on these attributes and building on them. And we also saw way back that just as in Unix, you can go and figure out when you fork processes, a process can figure out what its process number is. When threads are forked, a thread can figure out what its thread number is. And even though we tell OMP how many threads to create, we might tell OMP in one part of the code, and another part of the code might need to know how many threads were there. So that part of the code can make a procedure call to figure out how many threads there are. Okay, so these two are going to be relevant today. So we're going to look at reduction, and we need a problem to motivate what I'm talking about. And the problem we looked at way back before midterm was rounding. Okay? So we wanted to round up different elements of an array. And we want to do that in parallel. So this is basically same code. How rounding is done doesn't depend on what we are rounding. and we are looking at different data to round up, and actually there are different parts of the same big data structure. Okay? That's going to be key here. So, so this is what we want to do. We want to write one piece of code that is somehow thread aware and says, look, I want to do this work in parallel with so many threads. And this piece of code uh, basically allows multiple threads to be assigned different parts of this array that we want to round up. So the question really is, what do we do to make the code thread aware? What are the essential things we need? And again, if I was to give you this problem, in Java, you'd be able to give a solution that has some details and some concepts. So we want to tease out the concepts from the details. So we look at OMP. So here's a single threaded round. And all it's doing is basically going through each element of the array and rounding it up and storing that in the same element. Okay, so it's overwriting the previous element. And it's also printing out a trace here just for demonstrating the algorithm. Okay. So we can try to do this problem multi-threaded. I said we need to make it thread aware. So we are adding thread awareness in two different ways. We are first using OMP parallel to say that we want to execute this particular piece of code in parallel. Okay. And we are also indicating how many threads we want. But we don't want every thread to execute this block completely, okay, just as we did with the random. We want different threads to go and do different parts of this loop. Okay. So this whole reduction concept is tied to the notion of loops, and so it's not going to make your head spin like Paxos did. It's much simpler concept. In fact, lots of people argue that when loops are first introduced, we should also tell those students how parallel loops work. Okay, so this is actually being taught to CS1 and CS2 students. So we have lots of slides, but they should be easy to go through because we're talking of simple loops, and you basically understand concurrency. So it's combining loops with concurrency. Okay. So what we're doing in this loop is we are saying, okay, if we're going to execute this piece of code conditionally, and we're going to call a function called process iteration that decides whether a thread should really execute this piece of code or not. So this is going to be the key here. How do we decide? How do we allocate different iterations to different threads that have been created? Okay. And we want to look at it conceptually. So we're going to call this Boolean function process iteration. Let's say we wrote it ourselves. Later, we're going to go and see how this function can be provided automatically by OMP. So for now, just to understand what we need, let's go and figure out what parameters we might want to give to process iteration to allow these iterations to be divided among different threads. And the process iteration can then, based on those parameters, return some value, and we can have different implementations of the same process iteration. So I believe that is our first question. What parameters should be sent here so that we can go and do this code in parallel, ensuring that two different threads don't execute don't round up the same element of the array, and to also make sure that all elements of the array are actually rounded up. Okay, so what parameters do we need to process iteration? Okay, so we want to have a thread-aware float code here, and we're trying to determine the parameters. So we need a thread ID because we can make a decision based on the thread ID for sure. What other parameters do we need? Oops. Okay, I thought I had a student discussion slide there. I guess I didn't. Okay, that's too bad. So we'll probably see that later. So we can do that based on the thread number. We can figure out the number of threads and the loop parameters, the start index, end index, step size. Okay, given these parameters, we can imagine going and dividing the work. Okay. So here's my process iteration. It takes I, the index. It takes the initial value of I, 0. It takes the increment, 1. Okay. And it takes the length of the list, which is also going to be which determines when we stop, and it gives the process iteration which thread is executing this and how many threads there are. Okay. So that's my process iteration, and I can imagine different implementations of it. And here I'm basically just checking. I'm giving alternate elements of the array to alternate iterations to alternate threads, to successive threads. Okay, so thread 0 gets the 0th iteration, thread 1 gets the first iteration, thread 2 gets the so the third iteration, and so forth, and then we just cycle back. Okay. So with a process iteration method like this, we can control how the threads are assigned the iterations. But suppose the programmer doesn't really care and says, system, you just do something. I'll just tell you how many threads there are, and I'll say that in my parallel construct, and you do the division yourself. Okay, so supposing that's the goal. So let's try to figure out, and I hope I have a question here at least. How can we create a declarative parallel round, assuming that we don't really care about which thread is assigned which iteration? Okay. So the key here is that process iteration itself is problem independent. I didn't go and have anything about round there, but it does depend on loop. So how might we go in, and this is, there's multiple ways to do this, but supposing we were to design OMP and we know our constraints, we know how the syntax goes right now, how might I go and change the syntax to give OMP enough information to do something here automatically? Okay, so what additional attributes can be added to OMP to allow it to automatically implement process iteration? Okay, so all we've done is we assume that the statement that's being parallelized is a for. Okay, we're going to tie this to a loop rather than to a list. Okay, this way we can go and divide. This way we are more general. We can replace a list with a map. Maybe we needn't have lists. We might be just computing a factorial. So we don't have to go and bind ourselves to an array, okay, or list. And all I did was say, hey, treat this next statement as a for loop and give me for parallelism rather than regular for parallelism. Okay. So OMP does need to know all the information I mentioned earlier, but it can go and look at this for loop and figure that out. It can figure out what the increment is. You can figure out when to stop the iteration. It can figure out what the initial value is. Okay. So that's all you need to do. So conceptually, that's not what it actually does. It essentially goes and calls process iteration and computes those elements automatically based on information it has. Okay, it knows which thread is executing at any one time, and it derives this information from the for loop. Okay. So okay, so now what we're saying is that OMP not only understands what a statement block is, because it allows these comments or these annotations to be associated with pragmas, as they're called in OMP, to be associated with blocks, but it also understands what a for block is. Okay, so it's got to go and look at this header. And obviously, this particular for attribute makes sense only for loops. Okay, so if you don't go and attach this to non-for loop, then you're going to get an error. Okay. hopefully it'll be, it'll be an error that tells you what you've done wrong, but often the implementations just assume you don't make mistakes. Okay? So suppose you haven't made that mistake. You have indeed associated this particular construct with a for loop. Can you still imagine this making not sense for that for loop? So obviously this for attribute doesn't make sense for non-for loops. Can you imagine this for attribute not making sense for valid for loops, for real for loops for which a program for which? So this is my question. For, uh, give an example of a for loop for which such a program, such a uh, pragma. I should have said pragma, not program. Such a attribute does not make sense. So Leo said while loop, Jason said for each loop, and in C, when I first studied these loops, it was in the context of a language called Pascal, where for loops and while loops were different, and it was interesting. Leo's using the terminology I learned way back decades ago. But in fact, a for loop can be used to simulate what used to be called a while loop. And so while and for are wrong names, given that modern for loops can do different things, and while loops can simulate for loops. So when I teach, when I've taught 101 like courses, so basically the reason why it doesn't work for a while loop is because you can't pass loop index and other parameters to such a loop. What is the loop index? What is the start value? What is the end value? By looking at the header, you can't see that. In general, uh, systems cannot go and look at bodies because of the halting problem and understand much from it. So when I've taught loops, I've distinguished between counter control loops and event control loops. So counter control loops are loops where uh, we know the increment start and limit at loop entry from the loop header. Okay, so if you look at this code, we know what these values are. This would be these at the start of the loop, but we know by looking at the code. But by looking at the header, we don't know the number of times, what the index variable is, what the start value is, what the end value is, what the increment is. That's all sort of buried inside the piece of code here. Okay? And so this is a counter control loop that doesn't give the right amount of information. We needn't have counter control loops. We might have something more ambitious, which I call event control loops, where the number of times you execute the loop depends on some event that occurs after the loop starts executing. Okay? So if you don't have that information, you can't do this. And I've said that 101 like students go and use OMP parallel for. In fact, they really do. And but if they do make a mistake, they're going to be in trouble. Okay, so that is the biggest problem. Using these constructs is not an issue, but going and adding them at wrong places is an issue. So we've gone and added another attribute, which is for, and for can only be added to for loops and allows different iterations of a counter control loop to execute in parallel based on properties of the counter control loops, based on the header of the counter control loop. So we have another attribute. And we're going to add more attributes here with for loops. So in fact, the whole reduction idea is, like I said earlier, associated with loops. We use array examples because they make for compelling examples, but we needn't have an array in the loop. Okay, so how exact, now that we know what to tell OpenMP, let's assume that we are OpenMP implementers, and we need to figure out how to actually go and assign iterations of different threads. Okay. So we could do what I've done here. Okay, this which is use a round robin mechanism to go and assign slots to threads. I'm going to call this a closest distance approach. Thread 1 does this iteration number 1, which accesses, in this case, array element number 1. The thread 2 does access the second element. Round robin begins again, and thread 1 does the third element, and so forth, assuming 2 threads. If they're n threads, we can use an n. We'll have n different elements assigned to different threads. Okay, that's one approach. So the data structures being accessed by different threads are close to each other, but they're not the same. Okay, so we don't get into any consistency problems here in terms of program correctness. Or I could use the furthest distance division. Okay, so I could give this the first element to thread 1, the third element to thread 1, the second element to thread 1, and the fourth element to thread 1. So I'm keeping the elements far from each other. So if you have only 2 threads, imagine thread 1 being assigned from the top and thread 2 being assigned from the bottom. But if we have n threads, we have to basically divide the array into iterations into chunks and keep these elements as far away from each other as possible. So they'll both work correctly. But when we go and talk about keeping data structures near each other or far from each other, we get into performance issues having to do with locality. And those of you who've done operating systems should really understand, relate to that. And those of you who haven't, you should also have some intuitive idea of what's going on. Okay. So we need to make a comparison between these 2 approaches based on the locality arguments. And let me just remind you about locality. This is something that I assume you all know from a CS0 like course if nothing else, that data reside in disk, data reside in memory, and data reside in cache. Okay, and the size is of data that can fit in disk is more than what can fit in memory and what can fit more in cache. But the cost of accessing data here, accessing the larger amount of data is also higher. Okay. So that's what this is saying. So we want to make sure that so ultimately we want to be accessing data from cache, and we want to make sure that data as it migrates from disk to memory to cache makes as few transfers as possible during the course of computation. Okay? So we want to have as few transfers as possible for a given program. Okay, this is an objective. So we are trying to go and make our program more efficient or faster. Program should work either way. Okay? And this tells you about what happens when you transfer data from disk to memory. If you don't have enough space in memory, you go and take a unit of data called a page, you swap it out, and you replace it with stuff in disk. And memory happens to be a shared object among different processors. That's very important. This is what happens with the cache transfer. Caches tend to be per processor. So from the shared memory, they go to private caches. And just as there's a page unit, there's a transfer unit in memory called page. There's a transfer unit in cache called a cache block or line. So you take parts of the page and you transfer the whole thing. Okay. Now, because, and this ties our what's happening here with the consistency protocols that you guys are implementing and that we've studied. So caches are private and shared memory is shared. This the same data can be replicated, if you will, in different caches. Just as we saw in Paxos and two-phase commit and other synchronization algorithms, and in your assignments, that we can have replicated objects. Those are replicated distributed objects. These happen to be replicated non-distributed objects, okay, per processor. So we want to make sure that we don't have conflicts. Okay? Conflicts occur when we do writes. So whenever I go and write to a cache block that is also in a processor, when I meaning a processor, whenever a processor writes to a cache block that has data that has cached parts of memory that also cached in another processor, then we need to go and run a cache coherence algorithm, which is very much like the consistency algorithms we've studied. Okay. They tend to be a little different because we're not talking of network transfer, we're not talking of failures, but they're they're similar in spirit. Okay, and I've seen a zillion talks on different kinds of cache coherence algorithms. Okay. So reading from cache lines does not cause these algorithms to be executed, but we do want to make sure that we don't have to run these algorithms often. So we want to ideally make sure that we don't write to cache to pieces of memory that are cached in multiple processors at the same time, okay? That are cached in the same cache block to different processors. Okay? So this picture shows you how these transfers work. So let's say you really want to access some data A0 that's neither in memory nor in cache. Okay? You want to access A0, and you don't want to bring each of these words incrementally into memory. So you go and say, we assume that memory is exactly one page, and a page is of size 4 elements. So we bring all 4 elements into memory at the same time, because the assumption is that if you're going to access A0, you'll access A1 later and A2 after that. Okay? And then we go and cache part of the memory in a cache block, and we assume that that process of caching consists of exactly 2 words. Okay? So P1 can then access A0. Now T2 wants to access A0. The page is still in memory. Okay, and now it's got A0 accessed in its cache block also. So these two cache blocks are overlapping, or basically they have the same elements. And now if they both write to this, we have to have a cache coherence algorithm run. Okay, and this is where and this is a situation where it must run because they happen to be accessing the same location. So this is a true sharing conflict. Okay, so cache coherence algorithm guarantees consistency. What about this situation? P1 is accessing T1 is accessing A0, or P1 the processor, and this is accessing A1. But as far as the cache coherence algorithm is concerned, it works at the block level, not at the word level, just to make it more efficient. So it regards this as a conflict. It runs the cache coherence algorithm, even though this is false sharing. So consistency is maintained at the cache block level, and we have a notion of false sharing where processors write to different parts of the cache block, and they still execute a cache coherence algorithm. Okay, so this is the theory. This is what we know. Now we have to go and make a decision about how to go and divide elements among different threads. Okay. So I shouldn't say elements again. I should say iterations. This problem requires us the iterations to access different elements, but in general, we are talking about iterations. Okay, and we're going to motivate what we do, assuming that these iterations access different elements. Okay, because that's sort of the common case. So given what you know about cache conflicts, about page faults, cache faults, which do you think is the better approach? The closest distance approach or the furthest distance approach? Should we keep the data processed by different threads far apart or close to each other? Okay, and the real question is, what are the pros and cons, and why might you want to do something in between? Okay, so think about this. And let's, we'll begin with the closest distance approach and see what might go wrong there, and then look at the furthest distance to see what might go wrong there, and that might motivate something. Okay, so as David said, if we keep data next to each other, we have all these false sharing problems. Okay, we are making sure that different elements are being accessed by different threads, so we're not going to get true sharing problems here. Okay? But we will get these false sharing problems, so it'll be less efficient. And furthest distance approach, again, as David said, we won't have spatial locality. So let's say that T1 went and accessed A0, so it got this page loaded. Now T2 accesses A4. We have only one page in memory, so we must go and replace that page with T2's page. So we have a page fault, and then T1 then goes and accesses A1. We get another page fault, and the data are replaced. Okay, so lots of page faults. So as I implied earlier, the moral is that threads should really work on same pages, okay, on the loaded pages, but not write to overlapping loaded cache lines. Okay, if they are writing. If they are reading, it doesn't matter. So uh, in your assignment 2 and 3, you looked at the sum problem, and the sum problem summed up elements in a sequence. And when you're summing elements in a sequence, we are not writing to the sequence. We're writing to another variable, but not to the sequence. So that's why I chose round as a problem, because round actually involves writing. So how should iterations be automatically divided among threads? We need to give the programmer some control. Okay, the programmer knows, like I said, OMP only knows that it's doing iterations. It doesn't know whether it is an array-based iteration or not, whether it's writing or not, whether it's doing sum or round. So we need to go in, allow programmers some flexibility, and we'll go in, uh, start with something very simple, and then go to something complicated after that, as we see limitations. Okay, so what kind of parameters? Well, we can go and give it a step size. So this is not the step size of the loop. Okay, this is not telling you how much I should be incremented after each iteration. This says how many consecutive iterations are given to a particular thread. Okay, so that's a schedule. So 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 there are two parameters really. So we are talking about the schedule here, and the schedule takes two parameters. One is static. It seems that we'll have another parameter called dynamic later. We'll have to motivate that. But assuming static, that the number of iterations assigned, um, consecutive iterations assigned to a thread is constant, we just need to determine the size, number of elements in that block or step. Okay, and we can do this all. This is, I mean, the start of the loop. Okay, we don't really have to call process iteration in the middle of the loop. That was just something to show. That was something I presented to show you what logically happens. So let's see it at work. Supposing I have 7 elements, and I have gone and said static with a step size of 5. Okay. So the first thread gets 5 elements, and the second thread gets 2 elements. Okay. So there's this. So we see here something that's gone wrong. So if we forget about the step size, about page and cache issues, what's something that's obviously wrong with this schedule? So it's something wrong with assigning 5 here. Is it too obvious? Jason? Good, good. Okay. So the load balancing is another issue, and that is what we're going to focus on in the in the next few slides. Okay, how to balance work among the threads. The 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 cache and page size are not going to be something that we can look at from the problem itself. So we're going to look at this load balancing issue. Okay, and that's what's going to motivate different kinds of scheduling policies here. Okay, that problem wouldn't occur if we had a step size that is very small. Okay, we assign this here, this here, this here, this here, and then we're off by just 1. Okay, so we've seen that small step size can lead to cache conflicts. But why does OMP allow a step size of 1? It should just say never 1, okay, or never smaller than a cache block. So is it ever reasonable? Can you think of problems and where this would be reasonable? And I kind of answered this question already, but this just is testing how much how deeply you heard what I said. So some kind of problem where step size of 1 would be reasonable. So if you're summing a list, then adjacent reads do not conflict. Okay, so many problems require us to just read the list. So step size of 1 is fine in that case. Okay, so if we do static of 2, we have a compromise for the round problem that we are off by one only, and yet we were able to accommodate a bigger cache block. Okay. So we have to balance locality and load balancing. The word balance is used twice, no pun intended here. Okay, let's look at this situation now. T1 gets I1 and I2. T2 gets I3 and I4. So we're still working with 2. And now T2 is free and T1 is busy. And yet we go and assign I5 and I6 to T1. So, and assign I7 to T2. Okay, so we have this problem and we have a load imbalance with the same step size. So can you guys think of a policy name that would go and allow us to overcome this problem? So the name I'm looking for was dynamic, and you could have guessed that when I used the word static at one point. So new iterations assigned dynamically based on progress of previous iterations, and as Andrew mentioned, we could do this through a thread pool. Okay, so dynamic schedule would work like this. We assign I1 and I2 two iterations. We assign I3 and I4 two iterations. Now we've got to assign the next two iterations to somebody, and we'll assign that to T2 because T2 finished earlier. And if there's a thread pool, T2 would go and fetch I5 and I6 before T1 did, and then we can assign I7 to T1. So that's our dynamic policy. So dynamic is more flexible than static. Why not always support dynamic? Why not support this adaptive policy? Why allow the programmer to say, hey, I know better, so let's go and just do static, don't bother to do dynamic? Okay, and again, I'm assuming Andrew thought of the solution based on the implementation of A2 and A3. So think about A2 and A3 implementation and think about why we might not want to always use dynamic. Okay, so with static, we have no load balancing. We're load balancing here. So there's no shared data structure, no synchronization needed. So at the start of each loop, each thread can be told, hey, this is your first segment, this is your second segment, this is your third segment, and it can be given the start position of each of these segments, and it needs just that. Here we must, Andrew suggested we have a thread pool, or basically we have some kind of a pool of work, a producer-consumer problem. And in fact, the data structure could be something as simple as the next segment start. Okay? And after doing its work, every thread goes to this particular shared variable, which is synchronized. And as Leo mentioned, if we don't synchronize it, we are going to have race conditions. If we synchronize it, that leads to performance problems. Okay, because there are multiple threads updating this data structure. Okay, after you go and figure out what the next segment to start is, you take that work and then you go and you change this to the segment after that. Okay, so and unnecessary switches to the kernel, especially if the threads are executing concurrently on different processors, they have to unnecessarily go and make system calls. Okay. So let's go and look at this dynamic schedule here. I1 and I2. So we're going to try to show what may go wrong with dynamic. Okay, why we need even more dynamic than dynamic. So I1 and I2 assigned here, I3, I4 assigned here, I5, I6 assigned here. We've got 3 threads here now. Okay, I7 and I8 assigned here. Okay, I9 should be assigned to T2, and I mean the next segment should be assigned to T2, so it does I9 and I10. And now look at this. I1 and I12 have to be assigned, and they're assigned to T3. Okay, which means, and what we see here is that at the point at which T2 is doing I10, neither T1 nor T3 is doing any work. Okay, so between the time that I12 finished and I10 was picked up, there was some time lost, and during this time, these the processors were not used, even though they were idle. Okay, so T2 does I10 even though T1 and T3 were free before that. Okay, so we can, as a solution, we can always have smaller step or chunk size, but because smaller step size leads to better load balancing, so that would have solved the problem. But larger step size would lead to less overhead in terms of the number of times you have to go and look at the shared data structure, and also in terms of cache conflicts. Okay, so can we have our cake and eat it too? Can we have these advantages while not having this disadvantage? Okay. So what do we need? And so what might the solution be? Okay, so I think this is your student discussion slide. So anybody want to suggest something? So we're not being dynamic enough. We are dynamically determining what the next segment of work should be. Yeah, Jason? Right, that's what it did, right? T2 picked up its next piece of work when it was done. It picked up I9 and I10. So what we wanted it to have picked up I9 but not I10. So what's the problem? What's the constraint that dynamic and static both follow? Okay. What we need is a variable step size. Okay, which segments are picked is dynamic, but how big the step size is static. So that's the problem. We'd like the policy to automatically figure out and adapt the step size. So that gets us to what I would call dynamic plus plus, or what's called the guided policy. The step size changes dynamically based on remaining iterations after each assignment of work. Okay. So, guided means that the system does more, takes more decisions. And that could be done there can be many, many ways to do that. It could, in theory, decrease or increase dynamically the step size. But one policy that I read about is that it picks up the step size is proportional to the remaining iterations divided by number of threads. Okay, so let's see what that means. And like dynamic and static, there is a step size associated with the policy, and that is the least so that's the smallest size of the segment. Okay, so it'll never go below that. So in the beginning, we have 12 pieces of work, 12 iterations. So the thread T1 has to be assigned. So we go and divide 12 by 3, it evenly divides it. So we go and assign it 4 iterations. Okay. Now there are 8 left. We go and divide 8 by 3. We take the ceiling of that number and we get 3. Okay. So now we have 5 left, and we do something similar. We get 2. Okay. Now we have 3 left, and we give this choose size 1, and that is we can't go smaller than this. We can't conceptually go smaller than this, and this happens to be the smallest size. So I11 goes here, I12 goes here, and we see much better balancing here. That when I9 after it finished, T3 after finished work was not idle, and it went and got I11. Okay, so that's the guided policy. So this is guided step size changes dynamically based on remaining iterations after each assignment. Okay, so the guided policy seems to be overkill for the example I gave, rounding. And rounding is, of course, a very simplistic problem. But can you guys think, and this is, there's no right answer here, of policies where the guided policy of applications in which the guided policy would be useful? Something from real life or not so real life? Okay. So just imagine that we talked of parallelizing the grader, and we can imagine grading multiple assignments. I mean, near the end of the semester, we're going to have multiple assignments being graded about the same time. And we can imagine multiple tests. And we know those tests are sequenced, and they tend to have variable work. Some tests take a long time, as you've seen. Some take a very short time. Okay? So in general, in science, there are these irregular algorithms. These are algorithms that take different amounts of time for different iterations. And Jan Prince, who some of you might have taken a compiler course from, he's a world expert in parallelizing irregular algorithms. Okay, in fact, he teaches OpenMP in his advanced course for graduate students. Okay, so that's where this kind of policy makes sense. Okay, so we've seen parallel round, and threads write to different locations of array elements. And the problem you guys did in A2 and A3 was actually also a reduction problem, but it was sum. And the threads read different locations of array elements, and they write to a result variable. Okay, so we can do this here. Retval equals initial value, and retval is incremented with some element in the list, and different threads can go and execute different iterations, and the result in the end should be what you would get if only one thread executed this whole thing. Okay. So I can indeed write a parallel sum explaining what I've done before. But can you guys see a problem with this code? This is not safe. And if it's not safe, how might we solve the problem? So they write to a common variable without synchronization. Okay, that's the problem that Jason mentioned. He also gave a solution. I won't quite go to his solution directly. I'll go to another solution, and maybe he can tell, or somebody else can tell us what's wrong with my solution. Okay, we have OMP critical, so I just go and say OMP critical here, and I'm safe. I will compute the right value. Okay, this is not quite what Jason suggested. So why is this not efficient, and why? Why is it not efficient? So the computation is serialized essentially. Okay, so it's not, So there's no parallelism. We create all these threads, we go through the overhead of creating the threads, and they all execute sequentially. So alternative algorithm based on your A2 and A3 does not have to use OMP. So as Jason and Andrew both suggested, what we're essentially doing is divide and conquer. Okay, so we are going to take this problem that we had earlier, reduce it to two sub-problems. Each of these sub-problems is done in parallel. Okay, and then we go and combine the sub-problems later. Okay, so this is sort of the notion of reducing is of course comes from divide and conquer, that we reduce the problem to something else. Just as in recursion, we go and reduce the problem to a smaller problem, and then merge the result of the smaller problem with something we do. We're essentially doing something very similar here, and that's why I said reduction I first saw in the context of recursive programming, but it makes also sense in parallel programming because these two parts could be done independently, and then we could go and merge the results later. And so essentially what Andrew said was that we'd go and have each thread compute partial sums that have its own counter, and then these counters could be added up later to create the final value. Okay, so let's go and see what's happening a little bit more formally. So we have these sequence of elements, okay, and we have this operation plus, and I'll talk about string plus later. So I'm qualifying this by saying we are doing number plus. Okay, so these are our thread specific counters or sums that Andrew was talking about, and this is the final sum that we're going to have. So in parallel, each thread goes and gets an element from the array. It uses that as an operand to this binary operation here, plus the second operand is this result variable, second operand, and it goes and writes back to this variable the result. Okay, so this variable is both an operand and a result. That's why you have bidirectional arrow, and these could be done in parallel, and then we could go and operate on two other elements, and once we are done, now we have to go and access these two. Now we have to go and update this shared variable, and we could imagine going recursively and doing this also among making this parallel also. But the number of these variables is going to be order of the number of threads. So we're not talking about billions and billions of data that we are mining here. We're just talking about a few threads here. So we can probably do this serially without sacrificing too much. So we go and do this sum, and then we do this sum, and we've got the final value. Okay. So this is partial reduction, partial solution of problem. Maybe reducing it. Here's the reduced sum in private variable of thread. Okay, so these variables are private; they're not shared. And final reduction from these private variables, we compute this final. Okay, and this is a very interesting idea, that a problem that required us to go and synchronize on some variable was, or rather have a lock on some variable, allows us to go to a weight-free or lockless scheme by trading off, by using more space essentially, okay, by replicating this variable. Okay, so this is a very interesting idea, and I first saw this when I first heard decades ago Jim give his first talk on distributed computing, and I asked him the other day that did he invent this idea, and he said no, he borrowed it from somebody else and applied it to his context. But that's when I first saw this and said, wow, this is a really cool idea, that you can sometimes go to weight-free synchronization by replicating data. And this is not really replicating. It's not as if every change here causes a change here. You replicate the variable, you have initial values here, and later you go and merge the values if you need to. Okay? So the notion of weight-free or lockless coordination is something you'll see in the literature. You probably might see in industry also. So this is an example of that. Okay, just to see whether we understand things, I said that plus can be used in the context of numbers. It can also be used in the context of strings. So would this work if I'm trying to go and take these array elements and create a two-string operation where I concatenate all the elements of the array? Okay, so I'm arguing that this will not work. Okay, there's something different about plus string that will not make this work. Okay, so what's the difference? It is not. It is associative. So I should have just said it's not. It doesn't commute. Okay. And we need an operation that is that commutes and is associative. Okay. So in general, why do we need that? We are talking of some binary operation. Okay. Let T be the type of one of the operands of that operation. Then T must also be the type of the second operand and result, because what we're doing is we are taking the result and passing it as an operand, and the result also goes. So we not only get a value as a result, but we also pass it as an operand of the final reduction. And the final reduction is not going and distinguishing between threads and saying I will go and take your result first and your other thread next. Okay, if it was doing that, then maybe we can get rid of some of these constraints, but it's not doing that. So we need operation to be commuting and the associated. Okay. Okay, so that's what we have to do conceptually. Let's go and code that. So what we can do is have our shared variable, have our private variables. Okay, we know that we have two threads, so we create two variables, and what we're doing here is saying that depending on which thread is executing it, we go and change a different private variable. Okay, so we're always changing, we index using the thread number to index of this and changing that value. And in the end, this is the part that is parallelized. This is serial. So in the end, we go and take all of these values and sum them up and return ret val. Oh, I've got this void here. Okay, so ret val is the result, and either I should go and make this to be a float or change this. Okay. So I'm using this syntax here. This might work in the language. I'm actually using this undergrads implementation, and I forget whether I actually test this out or not. And not everything I'm talking about works actually in this implementation, so that's why I didn't catch this error. Okay. So let's look at this particular statement here. I'm arguing that this will work, but this statement here tells us that this will not work efficiently based on what we've already learned earlier in the lecture. Okay, and it has to do with cache issues. So hopefully you guys will get this quickly. So we do know, as Leo said, that an array, these elements will be stored in successive elements of the array, okay, in memory. So we do know that these are two different threads accessing consecutive elements. If they both happen to be in the same cache block, then we'll get fault sharing. Okay. So we need to solve this problem. Okay. And here's an idea. Maybe it'll work in Java. We don't use primitive values. We use objects. And as we know, objects are referred to by pointers. So my sum becomes not an array of consecutive floats, but an array of consecutive pointers. Okay. So if I do that, so let array consist of pointers, so reads go to writes go to non-adjacent. Reads will go to non-adjacent. So reads will certainly go to non-adjacent slots. Okay. So basically, these float values get put in non-adjacent slots. That's what I'm trying to say here. Okay. This seems to work, but I'm going to argue this doesn't really work. Okay. So why not? Okay. So float in Java is immutable. Okay. Because it's immutable, we create a new float on each sum. Okay. So that's the allocation problem and the garbage collection problem that David also mentioned afterwards. Okay. And the pointer is changed each time a new float object is created and assigned to this particular element. So this is the worst of all situations. So in fact, I was at a conference where they were talking of why Java is not conducive to parallel programming, and one of the problems was these immutable types here. Okay. That there was too much allocation. Okay, so fault sharing is adjacent slots assigned by different threads. So this is what we're going to do now. Okay, we're getting there, guys. I think we might even finish within about 10 minutes or so. So I've added some more concepts here. Okay, let's see what's going on. We've got a statement that's being parallelized, which happens to be, in this case, this particular block of code. Okay. There are some variables that are outside this scope. Okay. So before I go into detail, let me tell you what we're trying to do. We're trying to create a thread-specific variable in which we can create these partial results in such a way that the thread-specific variables are not in consecutive locations in memory and yet can be changed. Okay, that's what we're trying to do. And how could we do that? If we create these variables, for instance, in different objects, then we can ensure that. Okay, and the implementation I'm going to give you will indeed do that if underneath we are using Java. Okay, so we have to go and make sure that somehow the programmer is able to go and say that they want a replicated variable without actually replicating the variable, because we want the replication to be done by the system and let the system worry about creating the variable in replicas in different objects. Okay? So so we want OMP to control what happens to variables. So first, I'm giving you an example of a variable that OMP won't control. Okay? So this is the statement that's parallelized. There are some variables outside the statement, so that OMP won't do anything with. Then there are some variables that are inside this parallel construct. Okay, so this particular variable is inside this construct, but outside the loop. Okay, so it's not a loop variable. Loop variables will not be replicated, and this variable will be replicated. Okay, and if it's replicated, it might be so it might or might not be replicated. Let's put it this way. Okay, but these can be replicated, and whether they're replicated or not is controlled, and is controlled by this pragma here. So private says that we want the variable to be replicated. Okay, and if it's not private, it's shared and shared. I think it's shared. In that case, it is not replicated. Okay, so this is where what we control. And to imagine how this implementation might go, if you remember way back, which you probably don't, the way OMP was implemented by the undergrad was by creating a runnable class, of course, in which this code was executed. And the runnable class had to go and somehow access the global variables. And what he did was he went and made sure those variables are copied to the runnable and then copied in and then copied back. Okay. So what we can do is, rather than trying to go and, well, we can do something very similar with these variables. Rather than trying to make them all synchronized or synchronized and copying in and copying out, if they're private, we just go and keep them separate. Okay. And if they are shared, we do the same thing with these variables that we did with this variable. Okay. That's what I'm saying here. Okay. So now we are guaranteed that we don't have these cache conflicts. Okay. So we have private and shared be another attribute that we can add in our OMP declarations. Okay, so we have this two-level sum now, but this two-level sum is using the parallel construct directly without using for. Okay, so we have to go and use this process iteration. So the remaining slides are going to actually consider how we can get two-level reduction without process iteration. Okay. And to do that, let's go and see what's going on. And let's go and see what is specific to the problem and what is independent of the problem. Okay. So I have gone and highlighted various parts of this code. And I think I have a student discussion slide after this. Let's try to look at each of these blocks of code and see which of them are specific to some and which are independent of some. Okay, and before we do that, let's go and see how we might transfer this problem to a product solution. Okay, you don't want to begin with 0 here. Okay, so this is what you guys didn't get, but we do want to go and change both of these things. Okay, so again, both Chris and Jason made mistakes that you typically make when you're editing copied code. So how can we add more parameters to the for loop here? Okay, so we want to go and use for here. We want to add some more parameters so that we get rid of this process iteration, which is totally independent of the problem, as we saw. We didn't have to go and change that, and allow it to do all of these 3 steps. Well, no, we will write this step, and we want it to do this step and this step. Okay, and if we do that, then we won't make the kind of mistakes that Chris and Jason made of forgetting about this start and forgetting about the initialization. Okay, so that would be really nice. I mean, in fact, that was very nice to motivate this. That if we could just make it declarative, specify plus here, and give some more attributes to OMP to make that happen. And one constraint is that OMP will not go and look at this piece of code here. OMP will only look at the header here. It will not try to go and understand what code is executed. So what should I go and add to this particular construct here to make it implement its own process iteration? Okay. So we're going to do exactly what Chris said. We add a parameter. We go and say we're doing plus. Okay. And if it's plus, we know that the initial value will be 0. And if it's multiply, we'll say the initial value is 1. We also say that, look, we want reduction. Okay. And we need to also go and tell it, it's finally going to do the last step. It's going to create these private variables on its own. It's going to replace this variable with a private variable. Okay, so that's what it's going to do. And it needs to know which variable to replace. So that variable you go and mention here. Okay, and in the end, it has to go and compute, take those private variables, compute from them using this operation, the final variable. Okay, so that's 2 reasons why it needs this particular variable name. Okay, so we gave it these 2 things. And so private variable created before attributed statement entered for reduction variable. Okay, so that private variable is created before we go and actually do the for loop. And initialization, it depends on the operation. As Chris mentioned, plus could be 0, star could be 1. And all occurrences of reduction variable, this is the reduction variable, this is the reduction operator. All occurrences of reduction variable replaced with the private variable in this loop. And then after this loop parallelization step, we go through another sequential step. So we went through first a sequential step where we initialize the values. Now we go through a sequential step where we go and compute the final values. And we basically apply the same operation repeatedly, where using the values of these private variables we created earlier. Okay, so this is what we did for plus. This is what we did with star, and we made only 1 change. Okay, we did two changes. We also went and made this plus here. So this star better coincide with this star. If you don't, bad things are going to happen. Okay? Because this is the operation used for the final reduction, and this is the operation used for the initial reduction, and they better be the same. And you have to make sure that you make them the same. Okay, so we've got the essence of reduction. We will truly get the essence and migrate to the last section to be done tomorrow. If we can go and try to figure out how to substitute, how to have programmer-defined operations here rather than predefined operations. Plus and star defined by the language. What if I was to define my own operation with the properties we said operations should have earlier? Ideally, I should be able to have OMP do the same things with that operation that it does with plus and star. Okay. So that's my goal. So there are 2 questions. How should such operations be written? Are there any constraints on that? And how should OMP learn about these operations? Okay, because these are programmer-defined operations, so we have to go and tell OMP about them. We can't rely on OMP knowing about them as it knows about predefined operations. Okay, so let's try to answer each question individually. And let me give you 2 alternatives. And I'm going now from the sum problem that you did in A2 and A3 to the word count problem you also did in A2 and A3. So I said that I wanted to go and relate, my lectures today and tomorrow to what you did in A2 and A3. So this is a very direct relating. and we want to go and count the number of times a particular word occurs. Okay, there you saw the number of time a token occurs, but we can just say word. Let's assume that we're doing natural language processing, and this is an important problem for natural language processing. Okay. And I guess I should have had a close curly brace here, but I'm using my own syntax here to say that the words are these, and the counts are some map where each key is assigned the number of times that key occurs in this sequence. Okay, so A occurs twice, the occurs twice, and an occurs once. And here's my solution. Okay, I go and go through the elements of this sequence, okay, an array. I'm going to create a hash map. So I create a hash map, and I go and call a function called add with each element of the array that I'm looking at, plus the value 1, okay, as an argument. And I return this particular this hash table. And this is what add does. It takes an existing map, takes a key, takes a value, and if the key already exists, then so it goes and adds the value to a previous value if it exists, or nothing if such a value doesn't exist. Okay, and then it goes and associates a new value with the key. So this should work. This is one way of doing the problem, and this is a way I don't like. Okay, and why is this not a good way to write the map add operation for automatic OMP reduction? I can do it this way, but this is not giving this is not following the rules that OpenMP needs to do the reduction itself. So let's try to figure out why not. I think that may be the last student question I have here. So this is the last time you're to think at this late hour, but let's see. So both operands of reducible add should be of the same type, if this is the kind of binary operation we were talking about. Okay. So this is not the case. You should have 2 arguments, and here we have 3 arguments, and we need to have the second argument be the same as the result argument. Okay. So we're going to go and have a different operation, map plus, that we'll build in terms of this add already we have, and that takes 2 maps as an argument, and it basically merges them together. It takes each key of the second map and gets the value from that associated with the key, and takes that key value pair and sends it to the add function we wrote earlier. Okay, so that's how we would write our map plus operation, okay, which is not the same as add. And then I would do this reducible word count. So this is the word count that I'm doing that can be reduced. I'm doing the same kind of thing I did earlier, that I'm initializing the variable. Previously, I was initializing it using values of 0 and 1. Now I initialize it using this new operation, which OMP doesn't know anything about. And then I write this piece of code and go and do a new hash map. And Leo, I'll take your question later if I get a chance. I don't want to interrupt the recording right now. So I'll go and create this added value, and so I'll take this particular word and the value 1, create a new hash map associated with that, and do map plus a word count and added value. Okay. So the next question is, what information do we need to give OMP to allow it to do partial reduction and final reduction automatically? Okay, and the keys are these blocks that I've highlighted. Okay, and hopefully I have a student discussion slide where I can take Leo's question too. So this is what we do. Okay, and let's try to understand what's going on here. I have now these OMP directives being given both for the for loop and also for this new operation I've defined. Okay, I need to tell OMP about this new operation. I need to be able to use this operation later in my reduction. Okay, so my reduction will now go and use a new operation that's programmer defined. This is not star or plus. So I need for OMP to find the implementation of this operation. So I have to provide an implementation, and I have to go and tell OMP about the operation so that it can go and use it here. Okay, and OMP makes some decisions that might not be intuitive to you at this point. So you might think that it's asking for more information than you need, but let's go and see what's going on. So what did I do? I did do the previous sequential loop. Okay, I did create a new hash map for each word that I got. Okay, that because I need to go and need to create a new hash map operand, and what I'm given is an array, so I have to go and change that into this type. So this is just type conversion. And I did do these two operations also. Okay, and what I want OMP to do is not go and use this particular variable in while computing partial reductions, but I wanted to use a copy of this variable of the same type for each thread. Okay, as Leo said, we need to go and have private variables, otherwise we would go and get into synchronization conflicts. Okay, so I gave it the word. I went and told it what the variable is. That's word count. Just as I told it about sum, I tell it about word count. Okay, that's nothing new. Just as I told it about plus, I say map add. Nothing new here. So conceptually, our for loop is got the same complexity as before. Now, what should it do? So it can always find word count and allocate and figure out what its type is, and based on the type, it can go and create an object of that type. Okay. Well, we talk about how that's done also. Okay, so it can't quite do that. It has to figure out what class to use. So we need to tell it how to do that. Okay, but it can certainly create a variable of that type. So how did it find map add? It looks for one of these reduction annotations, declare reduction annotations associated with some method. And here we are saying map plus has the name map add to be used here. This level of, because it's not going to go and actually look at the header of methods. Okay, it does look at the header of a for loop. It doesn't look at the header of this method. If it did, our problem would be much easier, but it doesn't. So it says it just takes some arbitrary method and say, and it allows this to be associated with any arbitrary method and says, okay, you tell me what its name should be. So it says, okay, its name should be map add. So it says, fine, then I'll call you. Okay, whenever this map add is needed. It needs to know the type of the operands and result. Okay, so this is the type of the operands and the result. There's only one type we saw. It takes two operands of type T and gives the result of type T. So that's what this is telling it. Okay, it needs to know how to initialize this variable when it creates a private variable. Okay, map can be initialized using multiple implementations. So this is a statement that tells it how to go and initialize this variable. And by the way, this doesn't really exist in any language. This is my syntax based on what I've seen in C. I told you there's a Java implementation, but it doesn't implement this feature. So, but in general, here is some piece of code that tells it how to go and initialize this variable. Okay, it's not really looking at this piece of code and copying it. So this is what tells it. Now at the end, it's going to just call this map plus in the body. But the end is supposed to do a final reduction. In that final reduction, it's supposed to go and call this map plus operation. It has to know it's got the private variable and it's got the shared variable. It has to know which argument is the shared variable and which argument is the private variable. Okay? So this is what's being said here. This says the shared variable is the first argument to be passed to this function, and the private variable in the final reduction is the second argument. Okay, we could have a convention that the first argument is always a result and this is the operand, but this is giving you the flexibility of providing a syntax for it. Okay? So this is really crystallizing what reduction is all about. It's about creating private variables, it's about initializing private variables, that is, and knowing how to initialize private variables. It's about calling this function, knowing in what order to send the private variables and shared variables to this function. That's all made very explicit here, so we can understand how star and plus work based on how this is defined. Okay. So map add is corresponding to this map plus. Okay, and this map plus, they better be consistent. Okay, it doesn't really look at this map plus. It just goes and it replaces this word count with the private variable, but doesn't really look at it. But these should all be consistent. And I should this. So this type should be consistent with this type, should be consistent with this type, and consistent with this type. And this is the and the type is also used here. And this is the initialization. So before for loop, private variable initialized, and this is the OMP out corresponds to this particular shared variable that I said. Okay, that's the name of the shared variable, and it should correspond, which is also the name of this variable here. Okay, and OMP in is the private variable that's created, and it's also the variable that is passed to map plus when the final reduction is done. Okay, so after for loop, second level reduction carried out by calling map plus with the shared variable being passed in the position of the OMP out and private variable being passed in the position of OMP. And this is giving you the syntax of this reduction clause here, that you say OMP declare reduction. We have an operation name, operand type, and method name, and we have OMP out or OMP in here, or OMP out or OMP in here, and we have initialization OMP private equals some initialization operation. Okay, so so that's a general syntax here. Okay, I believe this method here corresponds. Okay, so we've got now some more syntax here with the reduction attribute. And very quickly, this is going to be an easy end. There are some default values. So OMP we want to parallelize the program as much as possible. So that if you don't specify number of threads, it just figures out how many processes there are. By the way, in Java, this is how you can figure out how many processes there are if you want to write a parallel program. And schedule, it assumes static. Step size, it assumes it tries to keep them far away from each other. So by default, if you don't give a static step size, it's a number of iterations divided by number of threads, so it keeps the threads far from each other. If you choose dynamic or guided, the step size is 1.